So the problem is the following. So if we're looking at the at our impulse response here, so if we go back to our h here, and we plot this here, then the problem is this function will continue in this direction here and also in the other direction. But this is just essentially chopped off here at this point here. So if I remove this here, so and we have this window function here, and so this looks a bit like an oscillation, and this oscillation getting bigger, the impulse response, and then it's getting smaller again. So something like that. So that's our h of n, and that's here n. So continue like this. But the problem is here, this opposite stops here at some point here. So and then this also stops here. But the problem is that this would continue here further, but the function is basically limited in its number of samples here. So it's essentially set to 0 beyond the samples. And so this then creates, if you're doing the Fourier transform here, creates this poor response here. Yeah, so if we have here our h of k, and here we have here the response, and then we have here this kind of ringing, and then it goes down, and we have here another ring with a ringing, and then it goes down, and we have here ringing again. And so here we have a poor 50 Hertz rejection, and here we have ripples. So we need to fix two things here. Yeah. So need to fix the ripples, and that's an S here, ripples, and we need to fix the stop band performance. So both factors are not ideal, and so how can we fix that? And so the solution is a so-called window function. So what does it mean, window function? So we have our original impulse response here, and we multiply this here with the function w here. So that's our window function. And with that we are getting a new impulse response. Let's call this here h new. And then this has hopefully better performance. In terms of in terms of ripples and stop band rejection. So stop band rejection. So the question is now obviously what kind of W of n could we take here? And so what's the idea now of creating this Wn to have a better response of that? So what kind of shapes of window functions? So general idea is to have a smooth transition to the smooth transition to 0. At the edges. So we had this already before when we talked about the Fourier transform, and so the idea is that the simplest window function is something like, if this is here the midpoint, so it's a number of samples this has, not W, not H, W of n, that this looks like that, for example. And this here goes to m-1. So that's the midpoint. We have something like this. So that's called a triangular window. So let's just get this function here in our script. So we don't need to filter anything just now. So we just move this, plot our HF here with a decibel in our script, so that we have this. So that's hopefully now the same response we had without. Okay, here we go. So here we've got our problem function. So just now damping is only minus 25 decibel, and we have here this ringing up here. So the question is now, can we improve this here in by adding window functions to it? And so let's see if we're able to improve that. So if we add here h equals h multiplied by numpy, and then Bartlett, and I just need to give it the number of samples here, and these are 401. So let's see if this looks now better. So we see we have a slight improvement compared to the other window here, because here this ringing now is gone and the damping is slightly better than before. So what are actually the performance criteria? Performance criteria for FIR filters. Remember, they are linear phase anyway, so that's a good thing. So we don't need to bother think about this, but there are other factors we need to discuss now. And so So remember what we also saw in the plot of our bandstop filter. So if we have something like this, E2j omega. So that's a realistic filter response. Remember, the bandstop would just go back up there, but we just have a look at this here. So then we see here, so we have ripple here. So that's called the passband ripple. Again, can be also expressed as just the amplitude ratio, but usually in decibel. And then of course we have the same here. So that's a so-called stop band ripple. And then here we have the transition width. Transition widths. And so therefore, if we are designing FIR filters, we would like to specify. Usually, we would like to specify the maximum amount of ripple here, the maximum stop band ripple here, or stop band rejection, stop band ripple or rejection, and then also specify the transition widths. So these are the criteria, or the different criteria we look at if we want to evaluate a filter, if a filter is good or bad. So back to our stop band filter. And let's have a look how different windows influence all these parameters. Yeah, so now test windows on our 50 Hz stop band filter. So let's see. Triangular window. Which is also called Bartlett window. That's obviously very simple. That just goes up and down here, and so what we see here, that ripples drastically reduced, yeah, but the stop band rejection is similar to the one without windowing. Is it really the case? Let's have a look here. And so if we do a proper comparison here, so we plot first our H without doing anything, and then we are applying Bartlett here to it, and we plot this into another figure.
So that's figure 2 and that's figure 1. And so we see here the difference. So also we see that the damping is pretty much the same. So a bit below minus 25 decibel. But what we see here, so the ringing is gone, but the stop band rejection is the same. So what we also see is here that the transition width, so how deep it goes, is slightly wider than in the rectangular window or in the no windowing condition here, but it's hardly visible. So a very popular function is the so-called Hanning window, and that's actually slightly wrong. It should be actually the Han window, because this is here actually Han is a Austrian meteorologist, Julius von Han. But usually in the English-speaking world, just called Hanning window. And so how does this window look like? So the window is defined as WH of n equals 2 alpha plus 1 minus alpha cosine of 2 pi n divided by m, with n in the region of m half and 0 otherwise. So if we plot that, so there's m half and there's minus m half, then this is essentially something like a cosine. I should mention the alpha factor is 0.5. So that's the Hanning window function. So let's try this here out. So if we replace the Bartlett here with Hanning, let's see how this looks like. And so here we see there's now a drastic improvement here. So that's again our figure 1 without any windowing, and then here we've got the Hanning window, which goes here down to roughly 56 decibel. And so we see already, if I get rid of this here, that we have a excellent stop band rejection. But we trade this in with a wider transition width. And but then also what is also much better is very little ripples. So in general, quite a nice window, and we see that just by applying this window function, that it's pretty impressive that we're able to improve the performance of our filter just by using this operation here. Okay, so let's move on to the Hanning window. Hanning window. So the Hanning window is quite similar to the Hanning window, but just that this alpha factor is 0.5054 and not 0.5. So it's just a slightly change of the function. Again, the response looks essentially like a cosine. Visually, that's an m half. It's minus m half. Visually, not much difference here. So that's our function here. But there's an interesting property of that. So if we look at our response, so if this is here h of k, then if we have our bandstop filter here, we will see that this will go like this. So here we have a semi-flat response here. So let's have a look how this looks like with these bumps, what we get here in Python. So if we replace the humming, so if we do that here and do the humming window, so then we see here these this response in the middle, where we have suddenly here this bump on the side. And so if we making a slightly wider transition width here, this might just repeat here a couple of times. So let's close this here again. And so again we have virtually no passband ripples, and but we have this so comparable performance to the HUN window. But the difference is, so the hunning window or the HUN window, the HUN window has the lowest point in the stop band, whereas the other one doesn't. So now finally the Blackman window. So the Blackman window is the one which has the best stop band rejection. So the Blackman window, without drawing the mathematical formula for this, but it looks pretty much again what we had before, that it looks like this here, but in this case here it's composed of two cosine functions. So let's have a look at the Blackman window. Blackman, so just restart this again just to be sure it's really the Blackman. It must be, because the damping of the Blackman is very impressive. So we see here
its damping is at minus 72 decibel, so it's a very, very strong performance, and it gives us an excellent stop band rejection here. So Blackman window gives us the best stop band rejection. But what we trade in for this is the widest transition width. That's easy to see when we compare this, especially with the condition with no window function in it. So let's just bring it here back up. So the Blackman window here generates us a slightly wider. It's very hard to see here in this scenario. Let's see. So that's here roughly at between 45 and 55. So if I do the same here, so then we see here that's a transition that we have here, very steep transition here, obviously with the ringing in it. But then on the other side here, so at the 45 here, this goes down very, very quickly. Whereas here, we see here we have got a massive wide transition here, going from 45 down nearly to 50. So it might be even that the full damping is not reached here because it's so slow here.